Welcome to the Sleepy Science channel. Here, we use soothing sleepy bedtime science stories to unveil the tranquil mysteries of the universe for you. Tonight, let's relax our minds and embark on a gentle journey into a world of science and dreams, surrounded by the 430 Hz Earth frequency. Can you believe it? At the edge of a black hole, you could look back and see a 360-degree wraparound view of yourself. This isn't magic. It happens because photons in this region follow specially curved paths as they orbit the black hole. What kind of mysterious force creates such a fantastical phenomenon? The answer lies in the mind-bending nature of black holes. Black holes are anything but ordinary celestial objects. They are like the ultimate cosmic beasts, lurking in the dark, boundless depths of space, quietly wielding the power to rewrite the rules of space-time. As we approach them and explore their edges, bizarre phenomena beyond common sense begin to emerge. Witnessing a 360-degree wraparound view of yourself is just one breathtaking glimpse among them. Let us now lift a corner of the veil shrouding black holes and glimpse the secrets of severely warped space-time. At the center of our Milky Way lurks an entity with a mass about 4 million times that of the Sun. It warps the surrounding space-time so intensely that within a range of 12 million kilometers, approaching light becomes trapped, unable to escape. This region, defined by the event horizon, acts like a mysterious barrier, sharply separating the interior from the rest of the universe. We call it Sagittarius Asterisk, a supermassive black hole. Some black holes are remnants of once bright, massive stars that shone gloriously. They often reside at the cores of galaxies and redefine our understanding of cosmic boundaries. When too much matter collapses under relentless gravity into an extremely tiny space, a black hole naturally forms. This is the inevitable result of gravity. Although matter feels solid to us, it is mostly empty space. Atoms consist of tiny nuclei surrounded by electron clouds. These electron clouds not only create the illusion of solidity, but also prevent atoms from getting too close. It is this repulsive force that allows you to stand firmly on the floor. The same force can also maintain the balance of a dying star or stars with relatively low mass, well below the threshold for forming neutron stars. However, when a star's mass reaches about 8 to 20 times that of the Sun, gravity gradually gains the upper hand, leading to the formation of a neutron star in its final stages. The surface of a neutron star exhibits incredible forces. Its gravity is about 100 billion times stronger than Earth's. Any matter landing on it is instantly compressed into a dense nuclear soup. If you were to fall onto a neutron star, the atoms in your body would be extremely squeezed. Electrons would be forced into atomic nuclei, combining with protons to form neutrons. These neutrons pack together tightly, supported by neutron degeneracy pressure, holding up a neutron star that can weigh up to solar masses. Yet this balance has a limit. Even a slight addition of mass allows gravity to take complete control, causing this city-sized star to collapse and ultimately form a singularity in space-time. As one cosmologist described it, the Big Bang singularity was a day without yesterday, the singularity born from gravitational collapse. is its opposite, a moment without tomorrow, leaving behind only a dark shadow of what once existed. A black hole, as we know it, when a star collapses into a black hole, a series of profoundly mysterious and astonishing physical changes occur. Meanwhile, beyond the event horizon, many enigmas remain unsolved. For centuries, our understanding of the universe was built on the foundation laid by Isaac Newton. He believed space and time were independent, immutable entities. Space was like a vast, static stage on which cosmic dramas unfolded, and time was an ever-flowing river, moving at the same rate for all observers. This intuitive, everyday perspective went unquestioned for a long time. Then, in 1905, Albert Einstein and his groundbreaking theory of relativity shattered this view, merging space and time into an inseparable whole. Space-time, the seed of this idea, sprang from Einstein's bold thinking. While pondering the constancy of the speed of light, an optical puzzle, James Clerk Maxwell's theory of electromagnetic waves revealed that in a vacuum the speed of light remains constant, regardless of the motion of the source or the observer. This directly contradicted the Newtonian intuition about relative motion. For example, when you run toward a sound source, the sound waves reach you faster, but light always travels through space-time at the same speed. To resolve this contradiction, Einstein reimagined the fundamental structure of reality. He proposed that measurements of time and space are not absolute, but depend on the observer's motion. To keep the speed of light constant, time must stretch or contract, and space must warp accordingly. This profound insight became the cornerstone of special relativity. One of the most startling predictions of Einstein's theory is the relativity of time. Imagine a spacecraft traveling near the speed of light. To a distant observer, clocks inside the ship would appear to tick slower than those on Earth. This is the famous time dilation effect. It is not just a subjective impression, but a real, measurable phenomenon, verified experimentally, such as in the Havila-Keating experiment in 1971, when atomic clocks were flown on commercial jets around the Earth. They showed a slight but definite time difference compared to stationary clocks on the ground, a vivid confirmation of Einstein's prediction. Moreover, space itself behaves unexpectedly at high speeds. Another key relativistic effect, length contraction, means that objects moving at very high speeds appear shorter in the direction of motion. For instance, to particles racing near light speed in the Large Hadron Collider, the 27-kilometer ring shrinks to just a few meters, a mind-boggling transformation. These discoveries show that time and space are not the rigid, universal background we take for granted, but are interwoven, highly malleable entities, forming a four-dimensional spacetime. Grasping this concept requires seeing every event, something happening at a specific point in spacetime, as a unique coordinate in this continuum. For example, when an astronaut steps onto the moon, it's not just a location on the lunar surface, but a combination of a specific time with a specific place. This inseparability of spacetime coordinates is key to deepening our understanding of the universe's nature. Einstein's brilliance lay not only in revealing how the separation between events depends on the observer's perspective, but also in discovering a quantity that all observers agree on, the space-time interval. This invariant acts like a magic key, uniting seemingly distinct space and time into one, revealing their profound, intrinsic connection, a realization that brings sudden clarity. Special relativity shows us a universe free from gravity's influence, a flat, uniform space-time, but Einstein knew this was only part of the story. In 1915, with general relativity, he introduced a new vision. Space-time is not rigid, but can curve and warp under the influence of mass and energy, taking on endlessly varied forms. Imagine space-time as a flexible rubber sheet. When you place a heavy object on it, like a bowling ball on a bed sheet, it creates a depression. Nearby small objects then roll along curved paths, not because of some mysterious pull, but because space-time itself has been reshaped by gravity's brush. Similarly, massive bodies like stars and planets subtly alter the geometry of space-time around them, guiding nearby objects along new trajectories. In this view, gravity is no longer a traditional force, but a natural manifestation of space-time's geometry. The concept of curved space-time has profound implications. In flat space-time, light that should travel in straight lines instead follows curved paths near massive objects, creating wonders like gravitational lensing. Light from distant stars and galaxies, bent by intervening masses, paints stunning arcs and rings in the sky, as if the cosmos is using its unique brush to create marvels. Einstein's equations also reveal a fascinating phenomenon. In stronger gravitational fields, time passes more slowly. This is gravitational time dilation. By placing precise atomic clocks at different altitudes, experiments have confirmed this effect. Closer to Earth's surface, where gravity is stronger, clocks tick slower, though minuscule in daily life. This time difference is crucial for technologies like GPS, where accurate correction of this dilation ensures positioning precision. Nowhere is the unity of space-time more evident than near a black hole. These enigmatic objects warp surrounding space-time so extremely that not even light can escape their grip. The event horizon of a black hole is a point of no return, where space-time distances stretch to infinity, rendering our familiar concepts of space and time irrelevant. To a distant observer, an astronaut falling into a black hole appears to slow down gradually, as if time stretches infinitely at the edge. Yet for the falling astronaut, time flows normally. This paradoxical phenomenon is a direct consequence of Einstein's equations. Under extreme conditions, space-time is not merely a backdrop. It is an active participant, governing planetary motions, light paths, and even galactic evolution. Space-time ripples, gravitational waves, first predicted by Einstein, were directly detected for the first time in 2015 by LIGO. These waves, triggered by violent events like black hole mergers, carry precious information about their origins, opening a new window into the secrets of the cosmic depths. Einstein's insight into the unity of space and time not only overturned our intuitive view of reality, but also sparked a profound philosophical shift. Time is no longer an absolute cosmic clock, and space is no longer a static and changing stage. Instead, they weave together into a flowing tapestry, shaped by mass, energy, and motion. This new perspective even touches the fundamental structure of existence. The holographic principle, for instance, suggests that space-time may be merely emergent from deeper quantum mechanical phenomena, a reality stranger than even Einstein imagined awaits our discovery. As early as 1916, just a year after Albert Einstein published General Relativity, Carl Schwarzschild found the first exact solution to Einstein's equations. This breakthrough work described the space-time geometry around a spherical, non-rotating mass, revealing a host of fascinating physical phenomena, including what would later be known as black holes, though the name wouldn't become popular until decades later. Einstein's general relativity fundamentally reshaped our traditional understanding of gravity. Gravity is no longer seen as a mysterious pull, but as a natural outcome of the curvature of space-time structure caused by the presence of mass and energy. Imagine a soft bedsheet. When you place a heavy object like a bowling ball on it, the sheet sags. A small marble near the depression naturally rolls toward the heavy object, not because the bowling ball is pulling it, but because the marble is following the curved surface of the sheet. Schwarzschild's elegant solution mathematically captured this phenomenon. It showed that space-time around a massive object is not flat, but curved due to its mass. This curvature intensifies as the object's mass increases. For small bodies like Earth, this curvature is very gentle, but near supermassive objects like black holes, space-time curvature becomes extreme, even forming boundaries from which not even light can escape. In general relativity, we use a mathematical tool called a metric to describe space-time curvature. It connects abstract space-time coordinates with the distances and times we actually experience in flat space. This metric reflects the familiar Pythagorean theorem. The distance between two points can be simply calculated from their coordinates, but in curved space-time, the metric must account for both the spatial curvature due to gravity and time dilation. The Schwarzschild metric was the first precise mathematical expression describing how space-time behaves near a spherical mass. It gave us a way to calculate how distances and times are stretched or compressed in the presence of a massive body. This theory not only transformed our understanding of gravity, but also laid a solid foundation for exploring extreme objects in the universe. To intuitively grasp space-time curvature, consider the Earth's surface. Although the Earth is round, over a small area like a soccer field, we hardly notice its curvature. Distances here can be calculated using simple plane geometry, but on larger scales, the Earth's curvature becomes obvious. Similarly, space-time may appear flat locally, but on larger scales or near massive objects like stars and black holes, its curvature becomes significant. The Schwarzschild metric further reveals that not only is space stretched around massive objects, but time is also dilated. This is why a clock near a massive star's surface ticks slower than one far away, a real manifestation of gravitational time dilation. Schwarzschild's solution introduced a key concept, the Schwarzschild radius. This radius defines the boundary around a massive object, where space-time curvature becomes so extreme that not even light can escape, forming a point of no return, known as the event horizon ... for the Sun. If compressed into a sphere with a radius of only about 3 kilometers, it would become a black hole. Its event horizon defined by this Schwarzschild radius. It's important to note that the event horizon is not a physical surface in the traditional sense, but a critical boundary once crossed. Irreversible fall toward the singularity begins, a point where space-time curvature becomes infinite and physical laws break down. Initially, Schwarzschild's solution described space-time around stars, but it provided a solid foundation for understanding black holes. By stripping away the matter inside the Schwarzschild radius, what remains is a pure black hole, formed solely by space-time geometry, its central singularity, representing the limit of matter density and gravitational strength. Space-time around a black hole is profoundly altered. As an external observer watches an object fall toward the event horizon, they see the object gradually slow down as it approaches the boundary, as if time is freezing at that moment. Yet, for the falling object itself, time passes normally, and it crosses the seemingly mysterious horizon without any dramatic sudden change. This space-time warping isn't confined to black holes. It leaves clear imprints in other astronomical phenomena. For example, gravitational lensing is a direct illustration. When light passes near a massive object, its path is bent by gravity, creating distorted or even multiple images of distant stars or galaxies. We often observe this around massive galaxy clusters, not only making cosmic landscapes more magical, but also providing scientists key clues to study matter distribution, including invisible dark matter. Moreover, the varying flow of time near massive objects has practical observational evidence. Take GPS satellites orbiting Earth because they experience slightly weaker gravity than on the ground. Their onboard atomic clocks run faster. To ensure accurate navigation data, engineers must correct for this subtle gravitational time dilation effect. These precise observations and applications demonstrate that Einstein's theory is not only philosophically profound, but also indispensably practical in real life. Although the Schwarzschild metric beautifully describes space-time structure around spherical masses, understanding the difference between local and global effects is equally crucial. Locally, space-time may appear flat, with objects following straight paths called geodesics, but on larger scales, these geodesics curve due to the presence of massive objects. It is this curvature that explains why astronauts on the International Space Station experience weightlessness. They are in free fall along the curved space-time shaped by Earth, although they feel no traditional force. The natural curvature continually guides them toward Earth, keeping them in orbit. The awe-inspiring power of Einstein's general relativity lies in its universality. From small-scale interactions near planets to celestial motions across vast intergalactic distances, all can be accurately described within this theoretical framework. The Schwarzschild solution is just one starting point among many specific scenarios. It paves the way for understanding more complex phenomena, such as rotating black holes, curved black holes, and charged black holes, Reissner-Nordstrom black holes, and general relativity's predictions go even further. Gravitational waves, ripples in space-time excited by accelerating masses, were first directly detected in 2015. By LIGO, this not only confirmed Einstein's prediction, but also opened a new door to exploring cosmic mysteries. One of the most counterintuitive aspects of general relativity is how it shows time and space intertwining and influencing each other, especially near black holes, where both are infinitely stretched. As an object falls into a black hole, from its own perspective, time flows normally, but to a distant observer, its motion seems to gradually slow, halting at the event horizon. This apparent paradox arises because time and space are not fixed backgrounds, but part of a dynamic structure, deeply influenced by gravity. To explain this, we can introduce the concept of geodesics. Objects always follow the shortest or most natural paths in spacetime. In curved spacetime, these paths are no longer the straight lines usually in vision. For example, light bending near a massive object isn't due to some extra force pulling it, but because it's traveling along a geodesic in spacetime warped by mass. This understanding of curved spacetime isn't just theoretical, it's vital in practical applications. Systems like GPS rely on extremely precise timing and positioning, and these technologies must account for general relativistic effects to function correctly. Meanwhile, studying spacetime warping also unveils mysteries of the universe's long history and deep structure. From the cosmic microwave background radiation, we can see how matter over billions of years gradually influenced and shaped the layout of space-time. At the heart of every black hole lies a mysterious boundary, the event horizon. This invisible threshold marks the escape limit for a non-rotating, spherically symmetric black hole. The event horizon's size is determined by the Schwarzschild radius, which is proportional to the black hole's mass. For instance, a black hole with the sun's mass has a Schwarzschild radius of only about 3 kilometers. External observers would see objects nearing this boundary slow down increasingly, their light redshifting until they finally vanish from view. Yet for the falling object itself, crossing the event horizon brings no sudden change. This seemingly contradictory phenomenon stems from the extreme warping of space-time near the event horizon, a magnificent spectacle predicted by Einstein's general relativity, inspiring endless wonder at the mystery and grandeur of the cosmos. A black hole is not merely an ultra-dense object, but a product of space-time itself warped by gravity. As you approach a black hole, the surrounding space-time is violently stretched and curved, especially near the event horizon, where the distortion becomes so extreme that distant observers find clocks near the black hole ticking exceptionally slowly, a vivid demonstration of gravitational time dilation. This phenomenon has been verified on Earth through atomic clock experiments at different altitudes. Once inside the event horizon, the nature of space-time transforms radically. It's as if the roles of space and time are swapped within the horizon. Gravity becomes as irresistible as the inevitable passage of time. All objects are doomed to fall toward the central singularity, as if their fate is already woven into the pulse of time itself. Imagine a scenario: 5 astronauts set out from near a black hole's event horizon, each choosing a different path. These paths leave distinct trajectories on the Penrose diagram, clearly revealing the mysteries of space-time geometry. One astronaut chooses to freefall naturally. Unaware they cross the event horizon. To them, the laws of physics seem entirely unchanged. Yet, within a single day recorded by their watch, their fate is sealed. They will inevitably reach the singularity, a point where space-time ends and density becomes infinite. Another astronaut, after crossing the horizon, resolves to resist fate. They ignite their rocket engines, hoping to counter the relentless gravity. Ironically, their struggle only accelerates their fall toward the singularity, shortening their remaining time. A third astronaut accepts destiny's arrangement, but makes a subtle adjustment to their course, allowing them to approach the singularity slightly faster, thus experiencing a bit more precious time than their escaping companion. Additionally, some astronauts linger outside the event horizon or choose to stay far from the black hole altogether. These diverse trajectories precisely demonstrate how, facing immense gravity, each individual's choices shape the unique imprint they leave in space-time. To a distant observer, as a spacecraft gradually approaches a black hole's event horizon, its behavior appears both mysterious and eerie. External clocks show the spacecraft's time seemingly slowing down, an effect of gravitational time dilation. As the craft nears the horizon, the light it emits stretches out, its wavelength steadily increasing. This is gravitational redshift, eventually making the light undetectable to the naked eye. In other words, from afar, the spacecraft appears forever suspended near the event horizon, as if frozen in time, never truly vanishing into the black hole. Once across the event horizon, the situation changes entirely. There, regardless of action, all paths inevitably lead to the central singularity. This is a fundamental consequence of space-time's structure. Unlike outside, moving forward within the event horizon means drawing ever closer to the singularity, as if space and time have swapped roles here. Forward motion is not merely spatial movement, but also temporal progression, guiding you toward the ultimate end. Any object entering a black hole undergoes a process whimsically called spaghettification. This vivid term graphically describes the extreme stretching caused by tidal forces. Near the black hole's singularity, the gravitational difference between an object's top and bottom intensifies drastically, stretching it into a long, thin, fragile form. This stretching occurs because gravity strengthens toward the black hole's center, creating a stark imbalance. However, a black hole's size influences this effect's severity. For supermassive black holes, with their large event horizons, tidal forces are relatively gentle. An explorer falling into such a black hole might not immediately experience spaghettification. In contrast, for smaller black holes, tidal forces near the event horizon are violently intense, swiftly stretching objects into slender shapes. Directly observing black holes is impossible, as their powerful gravity prevents even light from escaping. Yet this very elusiveness has inspired astronomers to use clever indirect evidence to reveal their presence. For instance, the Event Horizon Telescope (EHT), a global network of radio telescopes, successfully captured the first black hole image in 2019. That image showed the black hole's shadow, wreathed in glowing hot gas and dust, forming a stunning cosmic portrait. Additionally, by observing stars orbiting invisible objects like Sagittarius asterisk, scientists discovered these stars moving at incredible speeds, motions all pointing to a massive, dense object at the center. Black holes are regarded as natural laboratories for extreme physics, offering a unique opportunity to test general relativity under extreme conditions and explore phenomena like gravitational waves. Space-time ripples caused by violent motions of massive bodies were first detected in 2015 by LIGO, capturing signals from emerging black holes. This not only reaffirmed Einstein's predictions, but also opened a new window into the secrets of the cosmic depths. Yet the story of black holes extends further. Though often associated with powerful gravity and destructive force, at the other end of the physics spectrum lie captivating theoretical constructs like white holes and wormholes. Though these remain theoretical for now, they showcase the wondrous possibilities within space-time geometry, broadening our understanding of how space-time operates in extreme environments. White holes are often seen as black holes' mirrors. To black holes swallow everything into their inescapable event horizons, white holes do the opposite. They expel all matter and energy outward, refusing entry to any external material. Theoretically, the field equations of general relativity permit white holes, just as they do black holes. One can imagine a space-time region where all matter and energy continually diffuse outward, forming a zone that can never readmit outside matter, though mathematically self-consistent. No white hole has been observed in nature to date. The white hole concept actually arises from time-reversing black holes. They belong to the past rather than future-directed black holes. Penrose diagrams offer an intuitive way to understand this complex space-time structure. Take the Penrose diagram for a maximally extended Schwarzschild black hole. It depicts not only the black hole region, but also the corresponding white hole region. These diagrams, by compressing infinite space-time into finite graphics, enable clearer observation and study of connections between different regions. In such diagrams, the white hole corresponds to a past singularity from which particles or light radiate outward, crossing the horizon, separating the white hole from other space-time regions, though observers might detect traces left by particles erupting from the white hole. They cannot directly interact with the white hole itself. Wormholes are theoretical structures connecting to different space-time regions, often called Einstein-Rosen bridges, first proposed as a solution to Einstein's equations. They can be imagined as tunnels with two mouths connected by a slender throat, theoretically enabling travel between distant cosmic points. or even between different universes. The simplest wormhole model, the Schwarzschild wormhole, appears in the maximally extended Schwarzschild solution, but such wormholes collapse too rapidly to be traversable. Any matter attempting passage would not survive. In science fiction, traversable wormholes are common. Such idealized wormholes require exotic matter with negative energy density to maintain an open state, thus providing a relatively stable passage for travelers. Meanwhile, the maximally extended Schwarzschild spacetime not only reveals the black hole's mysterious visage, but also includes the theoretically corresponding white hole region, forming a fascinating cosmic model. This model divides the universe into 4 interwoven regions, each interconnected in novel ways that our conventional space-time notions, together composing the marvelous space-time geometry of Einstein's general relativity. In the maximally extended Schwarzschild space-time model, the universe is divided into 4 distinct regions, offering a fresh perspective on space-time complexity. The first region is our external universe, where observers reside, far from the black hole's extreme gravitational effects. Here, space-time still exhibits predictable and regular properties. The second region lies inside the black hole, an unavoidable domain leading to the future singularity. Here, space-time curvature increases drastically, and traditional physical laws break down. The third region represents an independent universe completely isolated from ours, a realm existing only through theoretical connections in the maximally extended Schwarzschild spacetime. Finally, the fourth region is the white hole's interior, symbolizing the black hole's counterpart, and like black holes that swallow everything, white holes continuously expel matter and energy. Linked to a past singularity, these regions are interconnected via a hypothetical wormhole, theoretically allowing an observer to travel from a black hole in one universe to a white hole in another. However, this journey remains purely speculative, as wormholes are extremely unstable, collapsing before any information or matter can pass through. This instability ensures that, within our current physics understanding, such passages are impractical despite limitations. The maximally extended Schwarzschild spacetime offers profound cosmic insights, revealing how black holes, white holes, and independent universes coexist within the same framework. This theory not only pushes the boundaries of traditional understanding of space-time and gravity, but also fuels our passion for endlessly exploring the universe's mysteries. In the realm of wormholes, space-time exhibits extraordinary and anomalous properties. For objects traversing a wormhole, they may experience an interchange of roles between temporal and spatial coordinates, a phenomenon quite similar to what occurs inside a black hole. The geometry of a wormhole is not static. Rather, it undergoes continuous dynamic changes due to the exotic matter required to maintain its stability. Mathematically, the Schwarzschild metric, which describes black hole spacetime, can be extended and generalized to incorporate the structure of wormholes. This theory reveals how spacetime can curve in an ingenious manner, seamlessly connecting regions that appear distant or disconnected. Such discoveries not only provide us with a novel perspective, for understanding the fabric of space-time would also inspire profound contemplation regarding the limitless possibilities of cosmic mysteries. Detecting wormholes or white holes poses a significant challenge. Although black holes themselves are invisible, they can be indirectly inferred through their gravitational effects on nearby stars and gas. In contrast, white holes are theorized to radiate energy outward without attracting matter, making them even more difficult to detect and identify. The issue of wormholes is even more complex. Their stability relies on large quantities of exotic matter with negative energy density to remain open, a form of matter that has not yet been experimentally confirmed. Moreover, many non-traversable wormholes collapse so rapidly that even if they form briefly, they may vanish before we have a chance to detect them. Some theories propose that wormholes may exist on microscopic scales. As part of the quantum foam, the fluctuating structure of space-time at the smallest scales. If such tiny wormholes do exist, they could play a role in the fundamental nature of space-time, perhaps even subtly connecting different regions of the universe. In fact, microscopic wormholes are thought to arise naturally from quantum effects. They might influence phenomena such as quantum entanglement, an idea explored in the E=EP conjecture, which suggests a possible intrinsic link between wormholes, Einstein-Rosen bridges, and quantum entanglement. Furthermore, in 1988, physicists Michael Morris, Kip Thorne, and Sevier proposed that an advanced civilization might be able to construct and stabilize traversable wormholes for interstellar travel. However, such wormholes would require vast amounts of exotic matter to keep their throats open and ensure a stable, usable passage. Although this concept remains speculative, it has stimulated widespread discussion about manipulating space-time and the potential future technology for crossing interstellar distances. The concept of white holes is closely tied to discussions about time. They symbolize the other side of time's one-way flow. Black holes are often associated with the future, seen as endpoints where matter and energy vanish, while white holes represent origins in the past, sources from which matter and energy emerge. This symmetry has not only theoretically inspired deep reflections on the relationship between time and the geometry of space-time, but also offers a fresh perspective on the nature of time's unidirectional flow. In 1963, mathematician Roeker discovered a solution to Einstein's equations describing a rotating black hole. This model introduced a more complex geometry than that of the non-rotating Schwarzschild black hole, now known as black holes. These rotating black holes possess unique internal structures and dynamic behaviors that have revolutionized our traditional understanding of space-time around black holes. Black holes not only demonstrate additional effects arising from rotation, but also provide a theoretical foundation for exploring the relationship between space-time and temporal symmetry, as well as potential connections between white holes and black holes. One of the most striking features of these black holes is their spin. This rotation challenges conventional understanding of space, time, and energy, Kerr black holes are defined by this spin, which not only determines their fundamental structure, but also makes them distinctly different from Schwarzschild black holes. While Schwarzschild black holes are perfectly spherical, Kerr black holes, due to their rapid rotation, are oblate, noticeably bulging at the equator. This distortion of space-time gives rise to several key regions. First, Kerr black holes possess two event horizons. The outer horizon marks the boundary from which nothing can escape, while the inner horizon lies close to the singularity, demarcating a region of distinct space-time dynamics. Moreover, outside the outer horizon lies the ergosphere, a region where space-time is dragged along by the black hole's rotation so strongly that nothing within it can remain stationary relative to a distant observer. Everything is forced to move in the direction of the black hole's spin. At the heart of a Kerr black hole lies the singularity, however. Unlike the point-like singularity of a Schwarzschild black hole, the Kerr singularity takes the form of a ring structure located in the equatorial plane, surrounded by highly complex space-time curvature. This rotational effect, known as frame dragging, causes the space-time around the black hole to twist along the direction of rotation, most notably near the ergosphere. Frame dragging has profound implications for the motion of matter and energy. Within the ergosphere, the dragging is so intense that no object can remain at rest. Everything is compelled to move with the black hole's rotation. Even light is no exception. However, under certain conditions, particles and objects can still escape the ergosphere's grip. This unique space-time effect illustrates the possibility of extracting energy from a rotating black hole, most famously via the Penrose process. This theoretical mechanism uses frame dragging in the ergosphere. A particle entering the ergosphere splits in two, with one part carrying negative energy into the black hole, and the other escaping with more energy than it started with. This elegant mechanism not only theoretically explains how energy can be extracted from a black hole spin, but also reveals the boundless possibilities inherent in black hole physics. Inside a Kerr black hole, the structure of space-time changes markedly, particularly in the region between the two event horizons. Here, boundaries delineate different space-time zones, forming an extraordinarily peculiar landscape. In this intermediate space between the horizons, time appears to flow irreversibly toward the inner horizon, making it difficult for anything that enters this region to escape. Beyond the inner horizon lies the core of the Kerr black hole, the location of the singularity. Notably, the unique geometry of the Kerr singularity suggests that it does not necessarily terminate all paths leading to it. Some trajectories may even bypass the singularity, theoretically connecting to other regions of space-time. This phenomenon not only challenges traditional understanding of the limits of space-time, but also reveals fascinating theoretical prospects for exploring physics under extreme conditions. Theoretical extensions of Kerr space-time reveal an exhilarating possibility. The interior of a black hole may serve as a gateway to other universes, forming an infinitely interwoven cosmic network. This concept stems from the special pathways within a black hole's interior, leading to the bold speculation that countless parallel universes may exist, all interconnected. Even more remarkable is that when a black hole's rotation speed exceeds a certain critical value, its event horizon may vanish, exposing the singularity. This state is known as a naked singularity. Without the protective barrier of an event horizon to conceal its effects, a naked singularity could exert unpredictable influence on distant regions of space-time, potential even signaling a breakdown of the laws of physics themselves. To address the theoretical chaos posed by naked singularities, physicists have proposed the cosmic censorship hypothesis, which posits that naked singularities do not form naturally in the universe. Although this conjecture has yet to be conclusively proven, it undoubtedly offers a highly enlightening theoretical perspective for understanding the inherent contradictions and tensions in extreme astrophysical phenomena. The ergosphere of a black hole represents a unique region of space-time where, as a result of the interaction between the black hole's rotation and space-time properties, states of negative energy can exist. To a distant observer, particles within the ergosphere may exhibit negative energy. This characteristic makes the ergosphere a site for energy transfer and various exotic physical processes, challenging our conventional understanding of energy conservation, while fully demonstrating the intricate appeal of rotating black holes in dynamic space-time structure. Detecting and studying black holes remains a major challenge in astrophysics. Although we cannot directly capture a black hole itself by observing its effects on surrounding matter and light, scientists can indirectly infer their presence. For instance, the distortion of orbits of nearby stars and gas clouds by a black hole is key to revealing the existence of a rotating black hole. By carefully analyzing these trajectories, astronomers can estimate the black hole's mass and spin. The rotation of a black hole not only influences the motion of nearby matter, but also determines the unique behavior of the accretion disk as gas and dust spiral gradually toward the black hole. Frame-dragging forces these materials to align with the black hole's spin, producing a series of observable features. Furthermore, when black holes collide and merge, they generate intense gravitational waves. These ripples in space-time carry crucial information about the black hole's mass and spin, revealing their inner secrets. Using advanced instruments such as LIGO and Virgo, scientists have not only confirmed the existence of rotating black holes through gravitational waves from mergers, but have also gained deeper insight into the spin properties and interaction mechanisms of black holes by analyzing subtle waveform variations. These groundbreaking discoveries have not only advanced black hole theory, but also deepened our understanding of physical phenomena in extreme space-time environments. Real black holes originate from the collapse of massive stars. At the end of their lives, these cosmic remnants vividly demonstrate the power of gravitational force. They are not hypothetical theoretical constructs, but products directly formed during stellar death processes, their behavior clearly influenced by their surroundings. To deeply understand the formation mechanisms and dynamics of these black holes, we must carefully study The factors governing stellar evolution, the dynamics of gravitational collapse, and the complex space-time geometry shaped by these processes. Throughout their long evolution, stars maintain a delicate balance between two opposing forces. On one hand, the outward pressure from intense nuclear fusion in the core. On the other, the ever-present gravitational force, pulling stellar material inward. This delicate equilibrium allows stars to burn steadily for millions or even billions of years. However, when a star finally exhausts its nuclear fuel, this resistance against gravity suddenly fails. For smaller stars, quantum effects play a key role. Electron degeneracy pressure halts further collapse, forming a white dwarf. For slightly more massive stars, neutron degeneracy pressure supports the core, giving birth to a neutron star. Yet when massive stars, with initial masses exceeding about 20 times that of the Sun, reach the end of their lives, even these quantum mechanical barriers cannot withstand the inevitable complete gravitational collapse, ultimately forming a black hole. During stellar collapse, the core rapidly contracts under its own gravity, while the outer layers of the star may be expelled outward in a magnificent supernova explosion, releasing astonishing energy and light. In this violent transformation, the core grows ever denser and hotter until it shrinks beyond a critical boundary, known as the Schwarzschild radius. Once this limit is crossed, an irreversible event horizon forms, a boundary from which not even light can escape, marking the birth of a black hole. The resulting black hole can be defined by three fundamental parameters: its mass, its rotational state, and, in extremely rare cases, its electric charge. These three parameters not only perfectly characterize the black hole's external appearance, but also reveal that, despite its extraordinarily complex formation process, its essential features can be succinctly summarized and understood. Black holes are often described as the simplest macroscopic objects in the universe. Because they have no hair, this metaphor implies that black holes do not retain any details about their formation process, whether a black hole is formed by stellar collapse, the merger of neutron stars, or through other mechanisms. Its final state is determined solely by three basic parameters: mass, spin, and, in extremely rare cases, electric charge. From the perspective of an external observer, all differences between black holes are erased by the extreme gravitational field, leaving only these most fundamental properties. As a black hole forms, the surrounding space-time undergoes rapid and drastic distortion. This distortion can be described by the Schwarzschild solution for non-rotating black holes, or characterized by the Kerr solution for rotating black holes. The Kerr solution, proposed by Kerr in 1963, provides a more realistic description, since most black holes exhibit spin. Due to the angular momentum of the collapsing star, it is this spin that causes the black hole to appear slightly oblate in the equatorial region and gives rise to phenomena such as frame dragging. The spin of a black hole distorts the surrounding space-time, particularly in the ergosphere outside the event horizon, where this effect is most pronounced. Within the ergosphere, all objects are forced to move in the direction of the black hole's rotation, and particles can even extract additional energy by harnessing this rotational energy. This theoretical mechanism is the basis of the Penrose process. Although the Penrose process has not yet been directly observed, it reveals the unique physical phenomena exhibited by black holes under extreme space-time curvature, offering a fresh perspective for exploring the mysteries of the cosmos. Gravitational wave astronomy provides direct evidence for the existence and properties of black holes, fundamentally transforming traditional understanding of them. When two black holes collide and merge, they release a tremendous amount of energy in the form of gravitational waves, which propagate through space-time at the speed of light. These ripples carry key information such as the mass and spin of the merging black holes, enabling astronomers to reconstruct these spectacular events. Observational data from LIGO and other detectors indicate that stellar mass black holes are quite common in the universe, with masses ranging from a few to several tens of solar masses. Supermassive black holes, with masses typically millions to billions of times that of the Sun, reside at the centers of most galaxies, including our own Milky Way. These behemoths likely form through the continuous accumulation of smaller black holes and gas. Their immense gravity not only dominates their immediate surroundings, but also profoundly influences the overall dynamics of their host galaxies. Supermassive black holes are usually surrounded by a hot accretion disk, where gas and dust spiral inward. Extreme temperatures generated by friction within the disk cause this material to emit intense radiation, including X-rays. By carefully observing this radiation, astronomers can infer the presence and basic properties of supermassive black holes. In contrast, stellar mass black holes are more elusive and are typically detected indirectly through their interactions with nearby stars or gas. For example, in binary systems, a black hole may draw material from its companion star, forming a luminous accretion disk, while the motion of the companion star also reveals the gravitational influence of the black hole. These phenomena provide strong evidence for the existence of an unseen black hole. Although the structure black holes appears simple, it conceals profound physical mysteries. At their core lies a singularity, where space-time curvature becomes infinite, and conventional physical laws break down. Surrounding the singularity is the event horizon, a surface that defines the boundary of the black hole for rotating black holes. There is also an ergosphere outside the event horizon. In this unique region, frame dragging forces space-time to rotate with the black hole, creating a distinct and highly challenging space-time structure. This not only demonstrates the powerful nature of gravity, but also continuously pushes us to reevaluate our understanding of space-time and the nature of singularities. Furthermore, black holes can influence their surroundings in dramatic ways. When a black hole accretes matter from its environment, it sometimes launches powerful jets of particles along its rotation axis. These jets, extremely energetic and approaching the speed of light, can extend far into cosmic space, profoundly affecting star and galaxy formation. Although the precise mechanisms driving these jets are not yet fully understood, it is widely believed that they are closely related to the immense energy released From the accretion disk and the action of magnetic fields, the ultimate fate of matter falling into a black hole remains an unsolved puzzle in astrophysics. Classical physics suggests that all matter inevitably reaches the singularity, but quantum effects may alter this outcome. The theoretical description of Hawking radiation reveals that black holes gradually lose mass and energy over time, suggesting that over extremely long timescales, black holes may eventually evaporate. However, this process far exceeds the current age of the universe. Although real black holes appear structurally simple, they continue to captivate and challenge scientists. Through ongoing observations with telescopes and gravitational wave detectors, we are able to glimpse the mysterious behaviors around black holes. Our cutting-edge theoretical research continually expands our understanding of extreme physical environments. From the immense gravitational effects revealed by stellar collapse to the formation of black holes, these objects are undoubtedly among the most vivid and profound manifestations of the deep laws of the universe. Black holes are not merely gravitational vortices from which even light cannot escape. They are also celestial systems that perfectly adhere to the fundamental principles of thermodynamics. This discovery has opened entirely new perspectives for deeply understanding the physical nature of black holes and their role in the universe. In the 1970s, physicists first proposed the theory of black hole thermodynamics. They were astonished to find that the behavior of black holes is closely related to the laws governing heat and entropy. The core concepts of black hole thermodynamics revolve around their event horizons. Research shows that the surface area of the event horizon does not merely define the boundary of a black hole. It is key to understanding its internal physical state. In fact, the area of the event horizon is proportional to the black hole's entropy. In thermodynamics, entropy represents the total amount of disorder and information in a system. For black holes, their surface area serves as a measure that records the information of all matter that has fallen inside. This extraordinary and profound relationship forms the theoretical cornerstone, black hole thermodynamics. There exists a remarkable parallel between the laws of black hole mechanics and the laws of thermodynamics, providing a crucial perspective for constructing a theoretical framework to describe the behavior of these extreme celestial objects. First, the zeroth law indicates that the surface gravity on a black hole's event horizon is uniform and constant. This aligns with the concept of temperature equilibrium in thermodynamics, implying that the black hole is in a state of thermal equilibrium. Next, the first law of black hole mechanics, analogous to the law of energy conservation, describes how minute changes in a black hole's mass, rotation, and charge affect the area of its event horizon. For instance, when a black hole accretes matter or merges with another black hole, its event horizon area increases accordingly. This phenomenon can be viewed as a direct reflection of how energy changes mirror the conversion between heat and work in a thermodynamic system. Most strikingly, the second law states that the total area of event horizons in isolated black holes never decreases. This resembles the principle in thermodynamics that entropy always increases or remains constant. For black holes, this means their size can only expand as accretion continues, unless energy is emitted through mechanisms like Hawking radiation, gradually reducing their size. Hawking radiation, a phenomenon predicted by quantum mechanics, reveals that black holes are not completely dark. In fact, due to quantum effects near the event horizon, black holes emit faint thermal radiation. This radiation causes black holes to gradually lose mass, leading to a slow reduction in their size. However, for most black holes, the timescale of this evaporation process is extremely long, so much so that in the current cosmic era, we cannot practically observe significant evaporation of large black holes. The third law of black hole mechanics is analogous to the third law of thermodynamics. Its central idea is that absolute zero temperature cannot be reached. For black holes, this means no physical process can reduce the surface gravity on their event horizon to zero. This limitation effectively prevents the formation of naked singularities. Within the framework of classical physics, the mathematical relationship between black hole entropy and surface area displays a unique elegance. The initial idea that black holes should possess entropy is credited to Jacob Bekenstein. He proposed that a black hole's entropy is proportional to its event horizon area. Subsequently, Stephen Hawking further developed this theory. Through precise calculations, he derived a formula incorporating Planck's constant, the speed of light, and the gravitational constant, revealing that the entropy value of a black hole is extraordinarily large. This implies that the amount of information it can encode is immensely rich. This groundbreaking insight not only completely transformed our conventional understanding of black holes, but also turned them from mere gravitational phenomena into physical entities with profound thermodynamic implications. One of the most remarkable aspects of black hole thermodynamics is the inverse relationship between a black hole's size and its temperature. Smaller black holes have higher temperatures and radiate more intensely, while supermassive black holes, such as those at the centers of galaxies, are extremely cold. In fact, the temperature of a stellar mass black hole is only a fraction of a degree above absolute zero, making its radiation nearly undetectable against the cosmic background radiation. The study of black hole thermodynamics holds profound significance. It skillfully brings together three often separate fields of physics: quantum mechanics, general relativity, and thermodynamics. Black holes provide us with a natural laboratory where, under extreme conditions, the intersection of different theories becomes apparent, thereby offering a unique perspective for uncovering the universe's most fundamental laws. In practical terms, black hole thermodynamics helps us reveal how energy behaves in extreme gravitational systems. By studying black holes, we have discovered that many of their underlying principles find analogues in other fields of physics. For instance, changes in entropy during high-energy particle collisions, or processes experienced in the early universe during the Big Bang, echo these fundamental laws. This not only highlights the universality of thermodynamic laws, but also demonstrates their broad applicability Simultaneously, the framework of black hole thermodynamics provides valuable clues to the ultimate fate of black holes. As a black hole gradually loses mass via Hawking radiation, the surface area of its event horizon decreases accordingly, yet this change does not violate the second law of thermodynamics, because the radiation released increases the entropy of the entire universe. This delicate balance between the decreasing area of the black hole and the increasing entropy of the cosmos perfectly illustrates how thermodynamic principles maintain internal consistency even under extreme conditions. Although black hole thermodynamics has achieved notable success in explaining many properties of black holes, several unresolved mysteries remain among them. A core issue lies in the microscopic nature of black hole entropy. In conventional thermodynamics, entropy is intimately related to the microscopic states of a system's particles. However, a specific microscopic interpretation for black hole entropy has not yet been fully elucidated. Some theoretical viewpoints suggest that black hole entropy may be closely linked to the quantum states of spacetime, but this conjecture remains an active area of research, requiring further theoretical and experimental support. Additionally, the mechanism by which Hawking radiation causes black holes to shrink over time, while theoretically established, is exceedingly slow for most black holes, making direct observational evidence currently difficult to obtain. Nonetheless, in-depth study of Hawking radiation has already driven significant advances in quantum field theory and inspired attempts by scientists to simulate analogous black hole conditions in laboratories. Hawking radiation stands as one of the most captivating phenomena in black hole physics. It overturns the traditional notion that black holes are completely black. In fact, black holes are not absolutely dark. Rather, they emit faint radiation near their event horizons due to quantum mechanical effects. This concept, first proposed in the 1970s, has now become a cornerstone of modern black hole theory. This process stems from the unique properties of quantum fields in curved spacetime, even in seemingly empty vacuum. Quantum fluctuations continuously generate particle-antiparticle pairs. Under normal circumstances, such a pair would rapidly annihilate each other. However, near a black hole's event horizon, the extreme gravitational field can capture one particle into the black hole, while the other escapes. The escaping particle constitutes what we observe as Hawking radiation, carrying away a portion of the black hole's energy, thereby gradually reducing the black hole's mass. Over immensely long timescales, the mathematical description of Hawking radiation integrates core principles from general relativity, quantum mechanics, and thermodynamics. Near a black hole's event horizon, the immensely strong gravitational field curves spacetime severely, thereby influencing the behavior of quantum fields and increasing the production rate of particle-antiparticle pairs. Since the event horizon acts as a boundary, escaping particles must overcome the black hole's gravity, a process that consumes the black hole's mass, gradually causing it to lose energy. For an uncharged, non-rotating Schwarzschild black hole, the radiation exhibits a simple, isotropic pattern. For rotating or charged black holes, influenced by multiple factors. Particle trajectories become more complex, and their radiation patterns correspondingly more diverse. Hawking radiation exhibits a purely thermal spectrum. Its temperature is directly related to the black hole's surface gravity and inversely proportional to its mass. This thermal nature is a direct result of the particle creation process, further reinforcing the view that black holes behave as thermodynamic systems. For enormous black holes, their radiation is extremely faint, making its signal difficult to capture with current instruments. Yet, the theoretical framework is exceptionally robust and has found analogs and verification in other fields of physics. As a black hole loses mass through radiation, its temperature gradually increases and its radiation rate accelerates. Eventually, near the end of its evaporation, it may undergo a violent radiative burst, perhaps even ending in a catastrophic explosion. However, for large black holes, the timescale required for this evolution far exceeds the current age of the universe, so it does not pose a practical concern in cosmic evolution. For hypothetical small black holes, such as those possibly formed in the early universe, the evaporation process could complete in a much shorter time, and their final bursts might provide direct observational evidence. Hawking radiation fundamentally relies on the interaction between quantum mechanics and the curved space-time described by general relativity. The core uncertainty principle of quantum mechanics allows energy fluctuations to continuously emerge from the vacuum, creating particle-antiparticle pairs near a black hole's event horizon. Due to the extreme curvature of space-time, these fluctuations can be distorted, enabling one particle to escape and become real. This phenomenon not only demonstrates the unexpectedly deep connection between quantum theory and general relativity, but also reveals the extraordinary properties harbored by black holes. Typically, these two great theories describe different levels of nature, but in the extreme environment of black holes, their convergence opens a new window for understanding the mysteries of the universe. Hawking radiation also overturns the traditional view that black holes can only absorb matter and energy, showing instead that black holes can interact with their surroundings in a subtle yet significant way. Hawking radiation demonstrates universality. This phenomenon does not depend on the specific size or composition of the black hole, but is rooted in the fundamental principles of quantum fields. In curved space-time, in other words, any system possessing an event horizon could potentially exhibit similar radiative properties. This universality has spurred enthusiasm for seeking analogous effects in other settings, such as simulating event horizons in laboratories using fluid systems, or exploring similar phenomena in other relevant physical systems. Furthermore, Hawking radiation provides crucial clues to understanding the life cycle of black holes. Although massive black holes grow by accreting surrounding matter, Hawking radiation over immense timescales limits their ultimate lifespan. As a black hole gradually loses mass through radiation, its physical properties and interactions with its environment undergo corresponding changes. Looking to the future, as the universe continues to expand and cool, even the largest black holes may eventually evaporate due to Hawking radiation, although this process lies far beyond our current observational capabilities. The evaporation of black holes is intimately connected to their thermodynamic properties. The emitted radiation not only signifies a loss of energy for the black hole, but also leads to an increase in the entropy of its surroundings, thereby ensuring the validity of the second law of thermodynamics. This delicate balance between the decreasing mass of the black hole and the increasing entropy of the universe vividly reflects the consistency of physical laws, even under extreme conditions. Although Hawking radiation has not yet been directly observed, its theoretical foundation is strongly supported by rigorous mathematical derivations and analogies in other physical systems. Scientists continue to explore new methods for detecting or simulating this process in controlled experiments, hoping to provide further evidence for this phenomenon. The study of Hawking radiation remains a vibrant and exciting field. It not only offers new opportunities to probe the fundamental laws of nature, but also continually challenges our understanding of the nature of space-time and matter, reminding us that much in the universe remains unknown and awaits discovery. The universe is not dead and silent. It is alive. Have you ever wondered if the universe is truly a cold, dark, and lifeless void? Are those distant galaxies merely isolated specks of dust, or are they nodes in a vast neural network, interconnected, resonating, and thinking? One bold conjecture suggests that perhaps from the very moment of the universe's birth, consciousness already existed. It might not be an accidental byproduct, nor a fortunate mutation on some planet, but rather, like space-time and gravity, a fundamental program of the universe itself. Our thoughts, memories, and emotions might just be a brief discharge in the cosmic brain, a faint yet unique brain wave. And the moment you look up at the stars, perhaps it is the universe seeing itself through you. This seemingly science-fictional idea is gradually becoming a topic of discussion at the frontiers of science. From this perspective, it turns out we are not simply thinking within the universe. Our thinking might be an expression of the universe's self-awareness. That is, we are the universe thinking about itself. If the universe truly possesses consciousness, then are we merely its observers, or are we a part of it? Could those precise physical laws stem from some unknown, deeper order? Perhaps the universe prepared the stage for life long ago, waiting only for us to appear. Perhaps we are not observing the universe, but the universe is examining itself through us. In that moment you gaze at the stars, you are not just an individual thinking. You are a node in a neural network spanning billions of light years, assisting the entire universe in a moment of deep self-reflection. Within this vast spatio-temporal network, the boundary between the individual and the whole begins to blur. You are both a cog that drives the machinery and the flowing thought itself. You are both created by the universe and participate in its creation. When we realize this profound connection between ourselves and the cosmos, we might understand that the key to unlocking the universe's ultimate mysteries has always been embedded within each of us, in our perception and understanding of the relationship between ourselves and the universe. So let us no longer say we are insignificant. Perhaps every one of us could be a manifestation of the universe's deepest, most momentary awakening of self-awareness. Have you ever considered that when you look up at the dark night sky, you might be seeing not just isolated stars, but a super neural network spanning the entire cosmos? Scientists have observed that under the influence of dark matter's gravity, billions of galaxies in the universe form a web-like structure. Some have noted that this distribution bears a morphological resemblance to the neural networks in our brains, like a spider weaving its web. Interstellar gas threads through space as filaments. Based on this striking morphological similarity, a mind-expanding question arises. Is the universe also thinking? Could we digest a fleeting thought in its vast mind? Of course, this conjecture currently lacks supporting scientific evidence and is based solely on morphological resemblance, yet, undeniably, the idea is profoundly compelling. Perhaps one day in the future, we will truly unravel the mystery. Is our brain comprehending the universe, or is the universe using us to comprehend itself? You might not expect that. Italian astrophysicist Franco Vazza and neuroscientist Alberto Felletti attempted to compare the human brain with the universe. Their research found that the two exhibit remarkable geometric similarities in their structural connectivity. This discovery has sparked widespread discussion. Although the brain operates via electrical impulses and the universe is held together by gravity and dark matter, both show certain similar features in their structural connectivity. In the brain, neurons communicate via long nerve fibers. In the universe, galaxy clusters are similarly connected by filaments of dark matter, forming a network structure of nodes and long, thin connections. This similarity across scales offers a new direction for contemplating the nature of the universe and the origin of consciousness. For instance, inspiring scientists to explore potential deep connections between macroscopic cosmic structures and microscopic neural structures, and whether the mechanisms underlying consciousness might possess a certain universality. However, it is important to clarify that, despite these similarities, the current findings are based solely on observations of surface structure. There is insufficient evidence to conclude that the universe is conscious. Building on this line of thought about deeper laws, could there be some fundamental cosmic principle that causes the micro and macro scales to follow the same underlying organizational logic? A bolder speculation: if our neural network can generate consciousness, could this cosmic superinformation network also be processing information in a way analogous to human thought, in a manner we do not yet understand? Galaxies communicating through gravitational pulls, whispers of electromagnetic waves, or even exchanging information via dark matter, which remains undetected by humanity. This leads to the question: is the universe processing information? If the answer is yes, then behind its operation might lie not just cold physical laws, but perhaps also a regulatory mechanism akin to sensation and will. According to traditional views, consciousness is a product of biological evolution, possessed only by higher animals. However, as a philosophical theory not yet scientifically confirmed, panpsychism proposes a hypothesis: consciousness may exist in matter in some primitive form. That is to say, The tiny particles constituting galaxies may possess a certain primitive, not yet understood property, analogous to the initial state of consciousness, like dormant seeds of awareness. Of course, this does not mean that stones can think or stars can weep. They do not possess emotional experiences like humans. Yet, when these particles continuously cooperate and connect throughout the universe, much like neurons forming a brain, it is possible that at a certain critical point, a higher level, unified consciousness might suddenly emerge. Based on this assumption, the ongoing particle interactions and material evolution in the universe could be seen as providing the conditions for the emergence and development of consciousness. It can thus be speculated that the universe itself might be an incubator for consciousness. Could it be that our human brains are one of the ways the universe uses to think about itself? When countless particles converge into galaxies, when galaxies connect into a cosmic network, and when you gaze at the starry sky late at night, are you, in fact, engaging in a subtle telepathy with the cosmos? What, then, is the essential nature of consciousness? American neuroscientist Giulio Tononi proposed the integrated information theory. This theory suggests that consciousness may be closely related to a system's ability to integrate information. However, this theory is still in the stage of scientific research and discussion and has not been fully verified. Simply put, the emergence of consciousness might not depend on having a brain, but rather on whether a sufficiently complex and tightly knit information network exists. Our brains are composed of billions of interwoven neurons. They constantly communicate, provide feedback, and coordinate, ultimately enabling us to think, feel, and possess the unique experience of self-awareness. This leads to the question, what if we apply this theory on a cosmic scale? Have you ever considered that the billions of galaxies in the universe might also be transmitting information to each other? For instance, the pull of gravity between galaxies, the traversal of electromagnetic waves, and the flow trajectories of dark matter. These all represent information circulation on a cosmic scale. From this, we might, based on theoretical assumptions, boldly speculate on the macroscopic scale of the universe. When interactions between galaxies reach a sufficiently frequent, dense, and complex level, could it, from the perspective of information integration theory, potentially give rise to a consciousness-like phenomenon at a certain critical point, much like neuronal activity? Extending from this bold speculation, one might infer that the entire universe operates like a super-large information processor, engaging in some form of self-perception in ways humanity does not yet understand. However, this view currently remains at the level of theoretical conjecture. Beneath similar appearances, could there possibly be some similar operational mechanisms at work? For now, however, this is merely a bold conjecture based on morphological similarity and has not been scientifically proven. Yet, it cannot be ignored that there are vast differences in their modes of information transmission and interaction. The neurons in our brains rely on electrical signals and chemicals for information transfer, which is extremely fast, both precise and rapid. In contrast, galaxies in the universe are primarily bound together by gravity. The transmission speed of gravitational interaction is relatively slow. A gravitational signal might take an immensely long time to travel. Some scientists, based on considerations of cosmic structure and black hole properties, have boldly proposed a highly imaginative conjecture within the vast structural system of the universe. The supermassive black holes at the centers of galaxies might play a role analogous to key nodes. Through activities such as accreting surrounding matter and absorbing radiation, black holes play significant roles in galactic evolution and the distribution of matter and energy. This brings to mind the crucial position of the central nervous system in the brain. During information transmission and processing, however, it is important to clarify that this analogy is merely a bold speculation based on functional characteristics. Currently, there is no scientific evidence to support that black holes can integrate and process information like the cerebral cortex does. In the seemingly tranquil universe, scientists speculate that the remarkable phenomenon of quantum entanglement may play a special role in cosmic-scale material interactions and information transfer in the quantum world. Even if two particles are separated by vast distances, a change in the state of one particle will elicit an instantaneous response from the other. This characteristic provides imaginative space for some unknown connection that might exist between matter in the universe. In this sense, the similarity between the nature of quantum entanglement and the cooperative functioning of brain neurons has sparked scientific conjecture about a connection between the cosmos and consciousness. What if quantum entanglement is not confined to microscopic particles in laboratories, but exists widely throughout the entire universe in some way not yet fathomed by humanity? If so, galaxies far across the cosmos might be able to communicate, forming something like a hidden quantum internet within the universe. The vast starry sky we see may be intricately connected through gravity and dark matter. The resemblance of its net structure to the brain's neural network offers a new perspective for scientific research. Imagine when we stand on Earth gazing at the stars, we are not seeing silence, but the heartbeat of the entire universe. Is it possible that the three-dimensional world we believe to be real is actually just an illusion, a projection of the universe onto a giant holographic screen? It sounds incredible, but this is precisely the core idea of the holographic universe theory in cutting-edge physics. This theory proposes that the universe is like a giant hologram. All the information of the universe might be encoded on a certain two-dimensional boundary. The three-dimensional world we perceive could merely be a projection of this information, an illusion separated from the true source code by dimensions. This is not merely science fiction. Some leading physicists have proposed the concept of the holographic principle and believe it might provide a potential approach to unifying quantum mechanics and general relativity, because it reveals a shocking truth. The essence of all things might simply be information. Once we accept the view that the essence of everything is information, we can't help but ponder, if the universe itself is a vast information network, Then could consciousness also be inherent within it, no longer a unique feature of life, but something long embedded in this holographic universe's information network, part of the universe's self-cognition? Speaking of consciousness, we often assume it exists only within the brain, but decades ago, Erwin Schrödinger, one of the founders of quantum mechanics, proposed a startling conjecture. Consciousness might not belong to us as individuals, but be a projection of the universe itself. He was the legendary scientist who proposed the Schrödinger's cat. Thought experiment, Schrödinger boldly speculated that our so-called independent self-awareness is actually just repeated projections and experiences of the universe's single conscious source. Each eye might be just a fleeting flash of universal consciousness. That is to say, when you are thinking, when I am feeling, when stars are twinkling, when a cat is sleepwalking. We appear as countless distinct individuals, but in reality, we might all be connected to the same ocean of consciousness. This is not mysticism, but a deep collision of science and philosophy. It brings a soul-stirring question. Who are you? Who am I? Perhaps we are all just the universe experiencing itself. What does that mean? You think you are an independent you. I think I live within my own consciousness, but in Schrödinger's view, based on a certain understanding of our self-experience, he speculated that these so-called separate selves are not truly separated at all, precisely because you and I each seem to experience only one continuous me. He inferred that the separated self might be just an illusion, like countless streams appearing separate from each other, yet all essentially originate from the same ocean. The I we believe ourselves to be might just be a universal consciousness playing its part in different bodies across different times and spaces. Even more startling, Schrödinger did not consider these mere metaphysical speculations. He believed this exploration into the nature of consciousness was not idle fantasy detached from physical reality, but rather key to probing the principles behind the material world. He therefore regarded it as the foundation underlying physics. In his view, metaphysics, that ancient philosophy studying the nature of existence, is not a subsidiary, but an important cornerstone for constructing the system of scientific cognition. So the question arises, what is real and who are you? Schrödinger proposed such a radically disruptive view. You are not you, I am not me. We are all the same consciousness in different shells, experiencing the world all selves. Might just be different facets of the same universal consciousness. This view, straddling science and philosophical thought, has sparked widespread controversy. It is like ... It is like sunlight passing through a crystal. Each colorful beam of light appears independent, but essentially they all come from the same light source, the same origin. You think you are an individual, but perhaps you are just one refraction of the universal consciousness. Although mainstream science at the time did not readily accept it, because this view was difficult to measure with traditional scientific instruments or verify through formulaic derivation, it acted like a seed, stimulating people's thinking. This view prompted widespread reflection. Some began to re-examine concepts like personal individuality, independence, the ego, questioning whether they are merely certain cognitive phenomena. produced by consciousness. The traditional view holds that consciousness is a product of the brain's complex structure and function. But with deepening research into consciousness and contemplation of the universe's nature, cognitive scientist Donald Hoffman proposed a highly controversial view. Perhaps when a system reaches a sufficiently complex and tightly interconnected degree, consciousness can emerge spontaneously. Yes, no one bestowed consciousness upon it. Rather, when the structure becomes complex enough, consciousness ignites by itself, like a spark. This theory features a crucial concept, phi, referring to the degree of information integration. Simply put, a higher phi value means that the various parts within the system can not only perform their respective functions relatively independently, but also cooperate efficiently when needed. For example, in our brain, visual neurons process image information. Auditory neurons process sound information. But when we see delicious food and hear it described, neurons from these different regions can rapidly work together through complex electrical and chemical signal transmission. They allow us to simultaneously produce integrated visual and auditory perceptions, and even trigger a series of thought activities like association and memory. This is the manifestation of a high phi value in the brain system. Just like our neurons, though dispersed, they cooperate with each other. It is precisely because of this that we can perceive the world, dream, and even fall in love with someone. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.